Hi people, this note is on angular velocity. And we're just going to dive right in and look at some examples right here. So in example 1, it says, assume the Earth is a perfect sphere with a radius of 6,400 kilometers. So it's asking us to find at what velocity in kilometers per hour is a person traveling on the equator. Well, in order to find velocity, we would always divide the distance by the time. And here we need to find the distance first. So if we know that the radius is 6,400, I want to find the circumference of the circle here. So here we know that circumference is 2 pi r. So here we can say that our circumference is 2 pi times the 6,400 right here. And then when I multiply the 6,400 by the 2, I end up getting 12,800 pi. So here we know that our circumference right here is going to be 12,800 pi. Well, that is going to be our distance right here. So to find our velocity, if we do distance over time, we can say that our velocity would be 12,800 pi. And then over time, so it's asking you how fast is a person traveling on the equator? Well, the Earth is going to rotate one complete revolution in 24 hours. That's what a day is. So here we know that this is going to happen in 24 hours. So now I just have to divide that out and it will tell me how fast a person is traveling on the equator. So I'll go ahead and type in 12,800 pi, and I'm going to divide that by 24, and here I get 1,600 and approximately 76 kilometers per hour. So we know that if you're on the equator, you are going around at a rate of 1,676 kilometers per hour. Okay. Then it says right here, at what speed is a person traveling at the North Pole? So technically, if you're right on the North Pole, you're not traveling at all, because no matter how much the Earth is rotating, you're not changing your position at all, right? So your distance here is going to be still 2 pi r, but if you're at the North Pole, the radius would be 0, right? So here we would say that this would be 0 kilometers, still would take 24 hours, so this would technically be 0 kilometers per hour. Okay, so now the next part is a little bit trickier, so pay really close attention right here. It says at what velocity is a person traveling in Guelph if Guelph is at 43 degrees north? So let's assume that this right here is where Guelph is. If this is where Guelph is, Guelph has a smaller radius to cover. Like the radius is different here because we're not on the equator, so this part of the sphere is going to be smaller here. So we need to figure out what the new radius is going to be. Well, if Guelph is 43 degrees north, that means that this is going to be 43 degrees. And remember, the central angle is equal to 43 degrees right here. So then what I would do here, in order to find this radius that I have here, so this is the radius that I want to find out, I'm going to draw in this right triangle right here. And then I'm going to kind of like zoom in on this right triangle so you can see what's happening here. So I'm going to put RG, so for Guelph's radius, so RG right here. Well, we know that this length right here is the actual radius of Earth. And we also know that it's going to be 6,400 kilometers, okay? And using the Z pattern, if this is 43 degrees right here, then up here, this angle up here will also be 43 degrees. So because we have this right here is the adjacent and this right here is the hypotenuse, we're going to use cosine using SOHCAHTOA. So we're going to say that cosine of 43 degrees is going to be the adjacent over the hypotenuse, right? So if I were to isolate the radius of where Guelph is, then I would end up getting, I would multiply both sides by the 6,400 to cancel it out. I would get 6,400 times the cosine of 43. Okay, I'm just going to write down approximately how much this is right here. So let's go ahead and calculate that. So 6,400 times the cosine of 43, and I get here approximately 4,681 kilometers. So we know that that's the radius of Guelph, of where Guelph is on the globe. But now to find the velocity, I have to do distance over time, but don't forget the distance is the circumference. So I'm still going to do 2 pi r, but this time my radius is not 6,400. It is this value right here, 4,681 kilometers. But because this right here is a rounded value, I'm actually going to use the exact value right here. So these are the same thing as each other, but this is rounded. And then this is the exact. So I'm going to plug in the exact value here. So I'm going to type in 6,400 times the cosine of 43. So that is going to be my distance right here. So remember, it's the distance, which is this, I'm not going to even type that into my calculator right now. I'm just going to say 2 pi times 6,400 cosine of 43. And then I'm going to divide that by the time. It's still going to take 24 hours to get, to complete a full revolution. So let's go ahead and type that into our calculator. So I'm going to type in 2 times pi times the radius, which was 6,400 times the cosine of 43. And then I'm going to divide that whole thing by 24, and I get approximately 1,225 kilometers per hour. So we can say right here, 1,225 kilometers per hour. Now, if you notice, depending on where you are in the globe, that will change the speed that you are traveling at. If you're on the equator, you have more distance to travel in the 24 hours. So your speed here is 1,676 kilometers per hour. If you are in Guelph or in a different part of the globe that is not the equator, you're going to be at a shorter, you're going to have a slower velocity because you have less distance to cover here than you would on the equator over here. If you're at the North Pole, you have no distance to cover. So if you're all the way directly at the top of the sphere, your velocity would have to be 0. These are all examples of linear velocity. Now we're going to talk about angular velocity. And angular velocity is the rate at which an object turns about its center of rotation. So how quickly it's turning around about its center of rotation. We use the lowercase omega to represent angular velocity. And so it's your angle divided by time. Another example here, assume that the Earth is a perfect sphere with a radius of 6,400 kilometers. So again, I'm going to draw out my perfect sphere. Okay, and if a person is on the equator, they're going around right here. In terms to find omega, we need our theta, our angle, and divide that by time. Well, here, this is completing a full revolution, which is 360 degrees, which in radians is 2 pi, and I'm dividing that by 24 hours. So when I reduce this right here, this would end up becoming pi over 12 radians per hour. That is the angular velocity. It means every hour you're covering pi over 12 radians. It doesn't matter how large or small the sphere is, it will always be pi over 12. Let's try to understand what's happening here, maybe with degrees, to kind of understand this a little bit better. So it's still theta over t, but if it's in degrees, a full revolution is 360 degrees. Divide that by time, which is 24 hours, you'd end up getting 15 degrees per hour. Okay? Now, let's skip question B and let's look at question C. What's the angular velocity of a person in Guelph? So now the person in Guelph right here is looking more like this right here. Less distance to cover, but the same angle measurement to cover. So the angular velocity here is still going to be 2 pi over 24, which is pi over 12 radians per hour, or 15 degrees per hour. It doesn't matter where on the globe you are, it's still pi over 12 radians per hour. So what does that tell us about the angular velocity at the North Pole? It's also going to be pi over 12 radians per hour. So that's the difference between linear velocity and angular velocity. Angular velocity is how big of an angle are you covering. So it doesn't matter the size of the shape that we're looking at, the angle is what we're looking at here, versus linear velocity, where the size Okay, so now the next example says a satellite circles the Earth in a circle 400 kilometers above the Earth's surface. So if we have, if I have kind of like a bird's eye view of the Earth's surface right here, or of the Earth rotating right here, this would be 6,400 kilometers. Then we have a satellite that's going around it. It's still going around in a circle. You all know I can't draw circles very well. Pretend like this is a circle right here. This is going to always be 400 kilometers outside of the Earth's rotation, okay? And it takes 75 minutes to complete a full rotation, a full revolution. So it says determine the angular velocity of the satellite in radians per second. So to find angular velocity, we're going to do the angle divided by the time. But in this example right here, it says that we want radians per second. So our time we want to be careful about right here. Our time here, it takes 75 minutes to complete a full 2 pi. So we know that our angle right here would be 2 pi. Again, it takes 75 minutes to complete it. But because it is in seconds, I need to convert my 75 minutes to seconds. So 1 minute is 60 seconds. So 75 times 60 would tell me that I would have 4,500 seconds. Okay, so to find my angular velocity, I take the full angle, which is 2 pi, divide that by 4,500, and we end up getting 0.0014. So it's completing 0.0014 radians per second. Then question B says, how far does the satellite travel in 1 hour? So this time we want to find the distance in 1 hour. So if you remember, it takes 75 minutes to complete this full revolution. So 1 hour, which is 60 minutes, it won't complete the full revolution right here. It's going to complete 60 out of 75 of a revolution, right? So for starters, I'm going to figure out, well, how much is a full revolution? So I'm going to do 2 pi r. So I'm going to do 2 pi times my radius. Now be really careful, because now we're trying to find the radius of the satellite's orbit. So we know if this is 6,400 and then we have another 400, that means that the full radius is 6,800. Okay, so this would be 6,800 kilometers. So multiply the 2 by the 6,800, I get 13,600 pi. So we know that it's going to complete 13,600 pi kilometers in 75 minutes. But I'm going to set up a proportion to figure out what's really going on here. So it's 60 out of 75 is going to equal my x over 13,600 pi. Now to isolate that x, I'm going to multiply by both sides by 13,600 pi. Gone. I'm going to multiply this side by that as well. So that means that x is going to equal 60 times 13,600 pi all over 75. I'll type that into my calculator. And I get 34,181 kilometers. So here we can say this is going to be about 34,181 kilometers. And that's my answer right here. Now, a quick note, don't forget that we know, I'm just going to zoom in right here, that the arc length is equal to theta times the radius. And here, theta is going to be, normally it would be 2 pi is a full revolution, but we're doing 60 out of 75 of that revolution. And then I can, so that's the theta right here. Then I can multiply that by the radius, which is 6,800. And then if I make this over 1, you're going to see here that I still get 60. So here's the 60. 2 times 6,800 is this 13,600 with a pi all over 75. So like you still get the same numbers when you multiply this together. So you would still get 34,181 kilometers. Okay. All right. That's it for this video. Let me know if you have any questions.